Hello and welcome. In this video, we're going to take a look at Green's theorem. And Green's theorem is going to relate a line integral to double integrals. We're going to be specifically looking at a curve that forms a closed, simple loop on the xy plane. And the area that is enclosed by that curve is going to be what we're looking at as a region for a double integral. So let's take a look. Green's theorem says, let C be a positively oriented, piecewise smooth, simple closed plane curve. It's hard to say that without laughing. There's a lot of technical terms there. So let's investigate that. Positive orientation is when we're going around, we want to think about the right-hand rule. The right-hand rule, if you're taking your right hand and putting your thumb in the direction of the positive z-axis, that is going to get us a counterclockwise rotation. Another way that we can think about that is it is going to enclose an area, and that region will always be on our left as we're traveling around this path. That's the idea of positively oriented. Piecewise smooth, well, smooth meaning that our derivative is always defined and our derivative doesn't equal 0 at any point in time. But being piecewise smooth would allow us to have something like a rectangle. As long as it's made of finitely many smooth pieces, then we have a piecewise smooth curve. Simple, that just means that our curve has no self-intersections except at its initial and terminal points. So this is going to be right out. A lemniscate is not going to be a simple curve. Closed is fairly intuitive. Our curve is simple, but it will have to start and stop at the same point in the positive orientation. And finally, a plane curve. This is plane, P-L-A-N-E. It exists on a plane. We'll be looking at the xy plane. With all of that in mind, let's look at the region that is bounded by C. Because we know we have a simple closed plane curve, that is just going to be a nice region on the xy plane. And now let's introduce our field. Our vector field, in terms of xy, is simply going to be P and Q as our x and y components. And that's going to be a C1 vector field, meaning that P and Q are continuous and so are their derivatives on the entire region containing C and D. Well, that means that our integral, our line integral here is going to be over a closed curve. So you'll notice this little circle there to indicate that this is a positively oriented closed curve. And our line integral can be replaced with a double integral, where we take the partial derivative of q with respect to x and subtract the partial derivative of p with respect to y and integrate over that region. There's our dA for integrating over a region. And if we wish to rewrite that, of course, this dot product, f dot dr, we can replace that with p dx plus q dy. Now, typically remember that when we are looking at line integrals, we need a parameterization of that line. And we would usually replace our dr with the derivative dr by dt, dt. Now, with Green's theorem, we can actually prove it just by showing that these two integrals are equivalent. But we can do that even in more efficient terms by just splitting this integral up into the component-wise parts, dx and dy. In order to show that this line integral is equal to the double integral on the right-hand side, it would suffice to show that this line integral, p dx, just looking at the x components here, is going to be equal to the double integral of the partial derivative of p with respect to y, with a little negative sign there, and also our second component, the line integral with q dy, is equal to the double integral of the partial derivative of q with respect to x. Now, the proofs of each of these components are very similar. That makes it a lot less work for us. We can simply show that this first equation in blue here is satisfied. And we can perform that by looking at really just evaluating this integral on the left, evaluating the integral on the right, and showing that they come up with the same expressions, but with opposite sign. Now remember, with double integrals, we evaluate them by turning them into iterated integrals. We could choose to iterate this dy dx, or we could iterate dx dy. Let's assume that we can iterate this as dy dx. Sometimes we refer to that as a type 1 region. Let's assume that this region enclosed by the curve can be expressed as boundaries of y, where y goes from a function of x, g1 of x, to another function of x, g2 of x. And then the boundaries on x should just be constants. And now I've also shown that I'm just taking the curve here and splitting it up into 4 little segments, and they should each be piecewise continuous. Now, of course, regions could be a lot more complicated than this. We may actually have to split that region up into several type 1 regions. But here I'm just taking a look as if that region was a single dy dx type region. Well, let's start off by looking at the line integral and evaluating it. The line integral on the left-hand side, the integral p dx, over the curve C can be split up into 4 separate line integrals over C1, C2, C3, and C4. Because you see how I've set up this as a type 1 region, over these regions, C2 and C4 are simply just vertical line segments, which means that their derivatives with respect to x are 0. And that would imply that 2 of these integrals should result in 0. We simply need to evaluate the other 2. Now, C1 and C3, those curves will still need to be parameterized if we wish to evaluate these line integrals. We can come up with a very convenient parameterization for C1 and C3 since they are functions of x. For C1, we'll just let x be our parameter. X is equal to x, and y is equal to g1 of x. And x would just simply go from a to b. Now, for C2, we can once again just let x be our parameter. Y would equal g2 of x, and x would have to go from b backwards to a. Now, of course, that might look a little bit backwards, but at least that will tell us how we should set up these integrals. Plugging our parameterization into p, x equals x, y equals g1 of x, with the parameterization from x equals a to x equals b. And for our second integral for C3, we will plug the parameterization in to p, x equals x, y equals g2 of x, and then our parameterization for x goes from b to a. Now these are backwards from each other, so we can fix that. We can actually write this integral as going from a to b so long as we negate the integral. That can be combined together. And then we've got a nice expression here, which is just a single integral with a single variable. Now, going back to the equation that we want to prove, on the right-hand side, we have a double integral. Let's investigate how we would take that double integral and turn it into an iterated integral. Well, as a type 1 region here, our boundary for y is going to be from g1 of x to g2 of x, where x is going to be bounded from a to b. Now, changing this integral over the region D into an iterated integral, we can put those boundaries on. And here I have the boundary for y from g1 of x to g2 of x, and the boundaries of x being from a to b. Okay, well, since I have the derivative of p with respect to y, and I'm integrating with respect to y, partial derivative and the integral cancel each other out, and I simply just need to apply the fundamental theorem of calculus and plug in y equals g2 of x and y equals g1 of x. And as a result, I end up with p evaluated at x comma g2 of x minus p evaluated at x comma g1 of x. Now, if you compare these two results, you see how they are identical except opposite in sign. And that is exactly what we needed to show. Now, similarly, our second equation can be also proven by expressing the region as a type 2 region, or iterating with dx dy. And I claim that that would then complete the proof, since the combination of those two integrals forms Green's theorem. Now, the proof, of course, is a little convoluted. We are essentially just taking that region that's bounded by that curve and treating it as a dy dx region and a dx dy region. And of course, that can be quite complicated to do in practice. Sometimes you would actually have to split it up into multiple double integrals in order to use dy dx or dx dy. But the concept here does actually show that we can take a line integral that meets these criteria and replace it with a double integral. And that brings us back to multivariable calculus before we even were really thinking about line integrals in the first place. So let's see where we can use this to evaluate line integrals. All right, in this example, let C be the positive-oriented curve shown in the picture here. Let's start at 0, 0 and proceed up the parabola y equals x squared until we get to the point 1, 1. And then we have a line segment to the left going to 0, 1 and a line segment straight back down to the origin. So we can tell right away that this is positively oriented because we are going in a counterclockwise direction, and we would be enclosing a region inside that's always going to be on our left as we travel around. It's also piecewise smooth, since we can break this up into 3 simple pieces that are all smooth on their own. We've got a simple curve, it's never intersecting itself, and of course it's closed and existing on the plane. Now with that, let's evaluate the line integral 3xy dx minus y squared dy. This would be our p and our q of our vector field. Well, by Green's theorem, we can turn this into a double integral. If we take the derivative of q with respect to x and subtract the derivative of p with respect to y, then we can integrate that function over the region D, which is enclosed by the curve C. That's a fairly nice easy function now. That just leaves us with negative 3x. But we do need to figure out how to turn this into an iterated integral. And that means that we need to come up with boundaries. Let's treat this as a type 1 region, since it's fairly straightforward to see the boundaries on y just go from y equal x squared up to y equals 1. And we can see that that is true for all values of x from x equals 0 to 1. So it makes it a nice, simple type 1 region. We could have also treated this as a type 2 region, where we see that the boundaries on x always go from x equals 0 to x equals the square root of y, for values of y going from 0 to 1. But since we already have our function given in the form y equals x squared, it might make more sense to write this iterated integral as dy dx. So we'll change that to the iterated integral, and we'll start integrating with respect to y. The antiderivative negative 3x with respect to y is negative 3xy, and that needs to be evaluated from y equals x squared to y equals 1. Well, that just gives us a polynomial in terms of x. And then we can find an antiderivative and evaluate from x equals 0 to x equals 1. This will finally result in just a single value. Now, of course, you could try this out by finding a parameterization of each of these 3 line segments and doing 3 separate line integrals, but that's going to take several more steps than just evaluating this as a double integral. All right, now I've set this next example up to show another property about vector fields. In this example, let's find the value of the line integral, where c is the positive orientation of the ellipse x squared over 25 plus y squared over 16 equal to 1. And our vector field is going to be 6x squared y squared 4x cubed y. Now this ellipse is going to be centered at the origin, and we can see its major and minor axes just because x squared over 25 means it's going to have a major axis along the x-axis of 5 units and a minor axis along the y-axis of 4 units. So if you want to maybe make a quick sketch, we can see what that would look like. It's going to be passing through the point 0, 4 and the point 5, 0. Okay, well, now let's set up the integral. Remember that this is going to be our p and our q. Using Green's theorem, we should be able to replace this with a double integral. And we are going to have to take the derivative of q with respect to x and subtract the partial derivative of p with respect to y. But of course, something interesting here happens. The partial derivatives here both are the same. They both cancel each other out. Now, that might not have been too much of a surprise because this vector field has a very nice property. We can double check here and see that the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. And that would imply that f is a conservative vector field. And remember, in a previous video we saw that with a conservative vector field, that if you have a closed path, then the line integral should equal 0. An example of that would be gravity, since we've seen that that is a conservative vector field. You know, along the Earth's surface, that gravitational vector field is pretty much pointing straight down. And I know that if I ride my bike up a mountain and then ride back down again, the work done by gravity overall is 0 because it's a conservative force. Same idea here. We've got a conservative vector field. We started and ended at the same point, so we should expect that the line integral equals 0 because we can interpret that as basically being like work. Now, another example, we can see that Green's theorem can actually be used in both directions. So let's take a look at an ellipse again, and let's actually try to calculate area. But let's calculate area by using a line integral. Now, this is just the general form of an ellipse, just like that last example. And remember that to calculate area of a region on a plane, we would just take the double integral of the value 1, dA. Now, this particular ellipse, we don't know what A and B are. We would either have to try to interpret this as an iterated integral of the form dy dx, and that would be okay, although we'll have to split this curve into two functions, y equals g1 of x and y equals g2 of x. We could also try to treat this as a dx dy iterated integral, and then we'd have to come up with x equals a function of y and x equals another function of y. It may have occurred to you to even try using polar coordinates. And that would be fine too, but this isn't exactly a circle, so you'd still have to have a little bit of carefully set up equations in order to translate this into polar coordinates. But here's our new strategy with this one. Remember that we are taking the double integral of 1. What if we were to choose a vector field, pi plus qj, so that the partial derivative of q with respect to x minus the partial derivative of p with respect to y equals 1. Well, then we'd actually be able to turn this into a line integral so long as we can parameterize the ellipse, and that's actually pretty easy to do. Now, there are lots of examples of good choices for this vector field. For this particular choice, I'm going to let the vector field equal negative y over 2, comma x over 2. Or if I want to factor that 1/2 out, 1/2 times negative y comma x. And you can double check. The partial derivative of x with respect to 1 minus the partial derivative of p with respect to y does equal 1. And that should allow me to translate this area problem into a line integral. What is the parameterization for an ellipse? Well, it's very similar to the parameterization of a circle. X equals cosine t, y equals sine t is a positive orientation. Only that would be with a radius of 1. Here we just have to make sure that x varies from positive a to negative a, and y varies between negative b and positive b. So in a very similar fashion, we can parameterize this ellipse as x equals a cosine t and y equals b sine t, from t equals 0 to t equals 2 pi. Now we'll need to plug this parameterization into our vector field, and we'll have to dot product that with the derivative of our parameterization. And then we can integrate that from t equals 0 to t equals 2 pi. Now, I've chosen this particular vector field so that it will fit the properties of what we need for area, but also so that this dot product works out to be a really convenient expression. This is simply just ab sine squared t plus ab cosine squared t, and we can take that 1/2 and factor it right out of the integral. But then we get to use the Pythagorean identity. Sine squared t plus cosine squared t equals 1. A and b are constants, so they can join the 1 over 2 out front, and we simply just need to integrate 1 from t equals 0 to 2 pi. And that gets us 2 pi, which cancels the 2, and ultimately our area equals pi ab. And this also fits with what we expect for a circle. A circle is just an ellipse where a and b are both equal to r, and then this formula would become pi r squared. And there we go. It gives you an idea of how we can apply Green's theorem in both directions. We can take a line integral and translate that to a double integral. We can also take a double integral, in the case of area here, find a vector field that would make that work, and actually translate an area problem to a line integral. Now hopefully that kind of blows your mind a little bit, because we're calculating area, which is a two-dimensional problem of the interior, into a line integral, which is really just talking about the perimeter. So Green's theorem is exciting in a way because it actually relates the interior of this region to the boundary of the region. And we'll take a look at that in future. If we go back to the actual formula here for Green's theorem, we'll see that this quantity, the partial derivative of q with respect to x minus the partial derivative of p with respect to y, that quantity there is called curl. And when we take a look at that later, we might be able to interpret Green's theorem again from a little different perspective, understanding what this idea of curl is. So stay tuned. Thanks for watching, and I'll see you again in the next video.